The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. All right, so eventually, today we're going to get into section 10.4, the first part of it. But before we do that, I had two students requesting basically the same question but different numbers, and I'm going to go through both of them. This is from section 10.2, part 2. And we have this picture of this lovely sailboat out on a lake with some greenery in the background. And it says this, it says, the matting around the picture has a uniform width. How wide is the matting if its area equals the area of the picture? Round to the nearest hundredth of an inch, assume X is 6 and Y is 4. And X was the top dimension of the picture and Y was the side dimension. So basically we've got this picture of a sailboat on a lake, and the dimensions of that, the area, which is length times width, would be 6 inches times 4 inches. So the area is 24 square inches. That's the area of just the picture. Now, it says, how wide is the matting if its area equals the area of the picture? So the area, let's see, we'll call this A sub P for picture and A sub M for matting. The area of the matting is also 24 square inches because they are equal. So the area total would be 48 square inches, okay? So the area of the picture and the matting is 48 square inches. Okay, now we're told that this matting has uniform width all the way around it. So let's see here, let's use purple. Okay, let's call this dimension right there X, which also means this dimension is X. It's X, that's the width all the way around the picture. Okay, before I go any further, any questions? All right, now, can you see that this distance right here would be X and this distance right there would be X? Does anybody have any issues seeing that? And this distance right here would be 6 inches. So that total distance, which is the same as the total distance down here, would be 2x plus 6, because you've got x plus 6, so 2x plus 6. All right, so the length of the entire thing is 2x plus 6. Any questions about that? Okay. Can you also see that this distance is x, and this distance is x, and this distance is 4 inches. So then this total distance here would be 2x plus 4. Any questions there? So now going back to this whole area equals length times width, we've got 48 inches equals length, which is 2x plus 6, times width, which is 2x plus 4. And that is our equation describing the entire picture, but included in that equation is x. When we solve for x, we'll be able to find that uniform width of the matting all the way around the picture. All right, are we ready to go on from here? So this gives us 48 equals 4x squared plus 8x plus 12x plus 24. 48 equals 4x squared plus 20x plus 24. I will subtract 48 from both sides. 0 equals 4x squared plus 20x minus 24. Okay. I'm going to take this second degree equation and I'm going to rewrite it on the next page, and then I'm going to solve it. So we've got 0 equals 4x squared plus 20x minus 24. Before I do that, though, I'm going to go back and double check things here. Let's see, that looks good. 24, subtract, I think we're okay. All right, well, I see that every term on the right has 4 as a common factor, so I'm going to reduce this thing down by dividing everybody by 4. So 0 equals x squared plus 5x minus 6. Okay. Now I'm going to use the quadratic formula to solve this. So a is 1, b is 5, and c is -6. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Continuing to simplify, x equals -5 plus or minus the square root of 25. And then we've got -4 times 1 times -6, which would be a plus 24 all over 2. X equals -5 plus or minus the square root of 49 over 2. X equals -5 plus or minus 7 over 2. Square root of 49 is 7. So we've got x equals -5 plus 7 over 2, which is 2 over 2, which is 1. And x equals -5 minus 7 over 2, which is -12 over, whoops, got ahead of myself there. Thinking of the wrong numbers, which is -6. So x equals 1, x equals -6. Now, because x is the width of the matting, it couldn't be a negative distance. So x equals 1 is the only correct answer. Now, in the original instructions, it said round to the nearest 100th of an inch. Okay, so x would be 1.00 inches. So this unit, this matting going around it is exactly 1 inch in width. All right, any questions about this problem before we go on? Okay, we're going to do another example here, and I'm going to, are we good? Because as soon as I click these things, it's all going to be gone. All right, so I'm going to do that, open it again. And now our dimensions are 7 inches by 3 inches. And we're going to go through the exact same process. Okay. So the area is length times width. The area is 7 inches times 3 inches, which is 21 square inches. That's the area of the picture. The area of the mat is also 21 square inches. So the area total is 42 inches, 42 square inches. Okay. Any questions there? Sorry, because I rebooted, things keep popping up on my screen, so I'm getting rid of them. Okay, now let's call that uniform distance x again. So that's x, and that's x. So that means this distance is x, this distance x is x, and that's 7 inches. So that would be 2x plus 7. And here this distance is X, this distance is X, and this is 3 inches. So this would be 2X plus 3. So using area equals length times width, 42 equals 2X plus 7 times 2X plus 3. Can you see how it's very same process, same process. So 42 equals 4X squared plus 6X plus 14X plus 21. 42 equals 4X squared plus 20X plus 21. Subtract 42 from both sides. 0 equals 4X squared plus 20X minus 21. So I'm going to recopy that on the next page. 0 equals 4X squared, what was it, plus 20X minus 21. Unlike the last one, this one I can't reduce. It doesn't have a common factor I could take out of all terms on the right side. So A is 4, B is 20, and C is negative 21. X equals negative 20 plus or minus the square root of 20 squared minus 4 times negative 21 all over 2 times 4. X equals negative 20 plus or minus the square root of 400 plus, let's see, we've got negative times positive times negative. That's where I got the plus. And 4 times 4 is 16. And that times 21 is 336. And that's all over 8. So X equals negative 20 plus or minus the square root of 736 all over 8. Now, let's see if 736 is a perfect square. If I take the square root of 736, it does not come out nice. Okay. Now, I don't need to get an exact answer. I just need to get an answer that's the nearest hundredth of an inch. So I'm going to go through and take negative 20 plus the square root of 736 all over 8. Let's find out what that is. So again, I've got to use parentheses around the whole numerator and around the radicand. So parentheses, negative 20 plus the square root of 736, close that up, close up the entire numerator, divided by 8. Uh-oh. Okay, let's see here. Let's try that again. Didn't like that. Negative 20 plus the square root of 736 divided by 8. And I'm coming up with 0.891. So rounded to the nearest hundredth, that would be 0.89. Okay. Now let's do the other one. X is negative 20 minus the square root of 736 all over 8. Can you see that negative 20 minus something else is going to be negative, divided by 8 is going to be a negative answer, so that one's not going to work. So we can save time. We don't need to bother with that. So that says that X in this case is 0.89 inches. And there you have it. Any questions about that one before we go on? Okay, let me just check something here really quickly. Here. Okay. All right, so now, let's see. We're going to move onward, and to do that, we're going to go on to section 10.4 now. And I'm going to switch screens, and we're going to look at this graphing screen. All right, and open up this one. All right, can everybody see my graphing screen, or have I got the wrong thing up there? Somebody?
We can see it.
You can see it. Okay, thank you. Thank you. All right. I just want to make sure. Sometimes I don't click the right buttons. Okay, what we're going to be looking at today is graphing second degree or quadratic equations. And I want to start out with a very basic one, which is just y equals x squared. Okay. And whenever I'm graphing some new kind of equation that I don't know much about, I tend to start by graphing using x values from -3 to +3. And then if I discover that, oh, that's not going to work, then I kind of go from there. But I tend to start with this. So now if y equals x squared, if x is -3, we'd have y equals -3, the quantity squared, which would be +9. Everybody okay with that? All right. If x is -2, we'd have y equals -2, the quantity squared, which is +4. If y equals -1, the quantity squared, we'd have +1. If y equals 0, the quantity squared, we'd have 0. If x equals 1, we'd have y equals 1 squared, which is 1. If x is 2, we'd have y equals 2 squared, which is 4. If x is 3, we'd have y equals 3 squared, which is 9. Notice something here. There's some symmetry going on in that we've got the same y value there and the same y value there and the same y value there. Okay. Now, plotting those points, let's see. -3, 9 would be about there. -2, 4 there. -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Now, obviously, either I've messed up terribly or this is not a straight line. Well, hopefully I haven't messed up terribly, but I can tell you this is not a straight line. Let's see if I can get a graph of this thing. Let's see here. Doesn't want to. There we go. Okay, whoops. Didn't quite make it. Sorry about that. Now, let's see here. Maybe I can. Don't want to spend 3 hours getting this graph perfect, but maybe just an hour and a half. How's that? Yeah, okay. Close. Anyway, that is what is called a parabola. Okay. Now, there are certain characteristics of a parabola that I want us to look at. Let's see, let's switch to red. Okay. Notice that this graph is symmetric about the y-axis. If we took what's on the right side and then folded it across or reflected across, it would match what's on the left side. So in this case, that y-axis is called the axis, helps if I can spell, axis of symmetry. I don't think I spelled that correctly. Tell you what, we'll just call it the axis of symmetry. That's how you get away when you can't spell. I think there's only one M, maybe not. Anyway, so the axis of symmetry. So the graph is reflected across that, okay? This point, which is the low point on this particular graph, is called the vertex. And we say that this thing opens upwards, okay? It's almost like it makes a cup that would hold water. All right, any questions about that? So now what I want to do, I'm going to undo some of this stuff I just did here. Unfortunately, it's going to take a little while, but that's okay. We can live with it. Okay, now, and let's erase all of this. Now, what I want to do is, let's go back to the red. I want to look at the graph of y equals x squared plus 3. Okay. And once again, we'll make a table. And we'll put in -3 through +3 in terms of x. Now, order of operations. In this case, y would equal what? -3 squared and then +3, right? What's -3 squared?
9.
And 9 plus 3?
12.
12. Good. Okay. Let's say x is -2. Y equals -2 the quantity squared plus 3, which is 4 plus 3, which is 7. Can you see what's going on here? How do these values compare to the values in the first graph, the y values? How do they differ?
They're bigger.
How much bigger?
Oh, by 3s.
By 3, right, because this is the same as that, plus 3. So 1
Yeah.
plus 3 is 4, 0 plus 3 is 3, 1 plus 3 is 4, 4 plus 3 is 7, and 9 plus 3 is 12. See what I'm saying? So I'm going to get the same outcomes plus 3.
Okay, got it.
Now, how does that affect our graph? Okay, let's see here. Let's get rid of these because we don't need these now. Go back here. Well, let's see. -3, 12 would be up here. -2, 7 would be up there. -1, 4 would be up there. 0, 3, 1, 4, 2, 7, 3, 12. And let's see what that picture looks like. Okay. And over here. They are, in fact, the exact same shape, except the red graph, how does it relate to the black graph?
It's higher.
How much higher?
3.
So basically, we could take the black graph and move it up 3 units and get the red graph. Everybody okay with that?
Yeah.
Any question? Okay. Tell you what, let's go to a green function. Let's say that y equals x squared minus 4. Okay. And again, we'll use x values from -3 to +3. All right. Now, I want to just cross this one out because I don't want us to be looking at that one. How does this compare to that?
It's 4 lower. On the
So
black one.
what would the y values look like compared to these?
5, -1, -4.
Wait a minute, wait a minute.
Oh, wait. From the first one to the second one.
Remember I said ignore this one.
Oh. First one would be 5, wouldn't
It'd be 4 less.
Yeah, so 9 minus 4 is 5. 4 minus 4 is 0. 1 minus 4 is -3. 0 minus 4 is -4. 1 minus 4 is -3. 4 minus 4 is 0. And 9 minus 4 is 5. Okay? All we did was take the y values and subtract 4. What's that going to do to the graph? How is the green graph going to compare to the black graph?
Is gonna be
Gonna lower it by 4.
Right. So in fact, I could do this 2 different ways. I could either look at these ordered points, ordered pairs, or I could take the black points that are there and move down 4. 1, 2, 3, 4. Let's see, there's -3, 5. 1, 2, 3, 4. There's -2, 0. 1, 2, 3, 4. There's -1, -3. 1, 2, 3, 4. You see what I'm saying? I could do it either way. And let's see what that thing looks like. Okay. So there's the green graph. So I could have just taken the black graph and shifted it down 4 units. Okay with that? That wasn't a rhetorical question.
Yes.
Yes, you're okay. Okay, so let's summarize here. Y equals x squared. Y equals x squared plus 3 goes up 3 units. Y equals x squared minus 4 goes down 4 units. Okay, so if we've got y equals x squared and we put a constant term out on the right side of that x squared, okay, if it's positive, it moves it up that many units. If it's negative, it moves it down that many units. Okay, any questions there? All right, let's go to the next page and let's start again with y equals x squared. And we had -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. I'm just copying the same table we had before, and that picture, let's see here, looked like this. Okay. Let's see here. Okay, so there's our y equals x squared again. What if I put a negative sign in front of the x squared? Now, order of operations, y would equal negative the quantity -3 squared. This, let's see here, let's go to a different color for a second. This negative sign is outside of the square. It's not -x, the quantity squared. It's not that. It's -x squared. Okay, so that means that I'm going to square it and then apply the negative sign. So what's -3 the quantity squared? What's negative 3, the quantity squared?
-9.
No, negative 3,
-3.
quantity squared is 9, right? Then you'd apply the negative sign, so your final answer is -9. You see what I'm saying? You'd square it and then apply the negative. So what are my y values going to look like? They're all going to be negative because you're going to square it and then apply the negative sign, order of operations. So what are all those y values going to be now? They're negative, aren't they? Except for 0. So what would the graph look like? It's going to open, oops, wrong place. Let me get rid of that one point there. That's in the wrong place. They're going to open downward. Having a hard time getting that thing to line up. I'm just going to freehand it. Okay. So if this is y equals x squared, this is y equals negative x squared. So putting a negative out in front flips it over. Okay with that?
Yep.
All right. Let's see here. Let's do this. Let's see if I undo this. Like that. And then erase this. Hopefully that'll save me some space. And now we're going to compare y equals x squared to y equals x minus 2 squared. So instead of the -2 being a constant outside that would move the graph down, -2 is on the inside. Let's see what that does to the graph. Okay, here's what I want to do. This time, instead of putting in x's and finding y's, I want to get the same y values as before. Okay? Consider what's going to happen. Okay? I'm going to pick some x value. I'm going to plug it in there. I'm going to subtract 2. And then I'm going to square it and get 9. What squared is 9?
3.
3. What else?
You could do, I mean, is that including the x minus 2?
Look, let me help you. -3 would also work, wouldn't it? -3
Yes.
squared. Okay. What I'm trying to get at is here, once we put in x, we're going to subtract 2 and then square it. So I need my x's to be 2 larger than those. Because by putting in x values that are 2 larger, what's the first thing that's going to happen to it? We're going to subtract 2. When we subtract 2, then we look just like that, right? I know this is a little crazy to kind of follow, but look and see what happens when I graph this. -1, 9, 0, 4, 1, 1, 2, 0, 3, 1, 4, 4, and 5, 9. What does that picture look like compared to y equals x squared?
It shifts sideways instead of up and down.
Exactly. How far?
Two points.
2 units. Yeah, yeah. So inside, putting a -2 actually moves it to the right, a +2. What do you think y equals x plus 3, the quantity squared, would look like compared to the black graph?
Would I move it to the left?
How far?
2 points or 2 units?
How far?
2 units?
How far?
Oh, 3. Sorry.
There you go. Okay. Yeah. All right. So what's going on? Okay. Let's go to the next page. So if we have a graph in the, one other thing, let's compare y equals x squared to y equals, let's go 3x squared. Okay. What's that going to do? -3, -2, -1, 0, 1, 2, 3. And this is what, 9, 4, 1, 0, 1, 4, 9. What if I put a 3 in front of x? Order of operations, you'd have 3 times -3 squared, which is 3 times 9. So what are these going to look like compared to those? You're going to square it and get this, and then what's the 3 going to do? Wouldn't it be 9 times 3 is 27, 4 times 3 is 12, 1 times 3 is 3? Because you'd square it, get the results, which look just like those, and then you'd multiply times 3. So these y values are 3 times those y values. Are you seeing that?
Yeah.
So and I'm just going to kind of slop it out here for the sake of time. So let's say this is the original graph. This new one is going to climb steeper, faster, okay? Because your y values are going to be 3 times as much. All right, so I want to jump to the next page and kind of summarize all of this. Let's say we have an equation in the form y equals a times the quantity x minus h squared plus k. All right. What happens? The k moves things up and down. If k is positive, the graph moves up. If k is negative, the graph moves down. We looked at that first. What happens on the inside? If h is negative, if it's minus h, it moves in a positive right direction. If it's negative h, it moves in a left direction. If a is positive, it opens up. If a is negative, it opens down. If a is like 2 or 3, it climbs steeper. If it's negative 2 or 3, it's flipped over and falling steeper, so to speak. What I want to look at is y equals x squared. The vertex is at 0, 0. So for y equals x squared, it's like we've got y equals 1 times x minus 0 squared plus 0. Writing it in this form, where a is 1, and there's no shift to the right or the left, and there's no shift up or down. The vertex is at 0, 0. Okay, that goes back here. Okay, now take a look at this graph, x minus 2. H is 2 and K is 0. And the vertex is at 2, 0. Let's go back here to this one. H is 0 and K is -4. The vertex is at 0, -4. And I know I'm kind of going quickly on this. What I'm trying to get you to see is that when you've got something in the form y equals that, oops, that's okay, the vertex is at HK. So let's say, let me look at some other examples here. Let's say we've got y equals x minus 3 squared plus 4. The vertex is at HK. Because this is x minus h squared plus k. All right. So the 3 moves it 3 to the right, the 4 moves it 4 up. So from here, we're going 3 to the right and up 4. So our vertex is moving over to HK. Are any of you getting this?
Yeah. Sort of.
Kind of.
Kind of, okay. Let's say I've got y equals 2 times x plus 3 squared minus 5. So h would be -3 and k would be -5. So the vertex is at -3, -5. Because this would be x minus -3. Inside, inverse, outside, obvious. It's gonna be the opposite of, or the inverse of that. So -3, and then what's obvious there. Okay.
So
Now-
if K is negative, then H has to be negative?
No. K and H are totally independent of each other. It's just that here, okay, if I've got a times x minus h squared plus k, k is -5, but h isn't 3 because this is x minus h. How could you write x plus 3 as x minus? It'd be x minus -3.
I don't know.
It's the inverse of what's inside. Let's take a look at another one. Let's say I've got y equals x plus 8 squared plus 3. H would be -8. K would be 3. The vertex would be at -8, 3. It's the inverse of what's inside and obvious of what's outside.
Okay, so you just flip it. Or,
Right? You don't flip it. You're not doing the reciprocal. You're doing the inverse of it or the opposite of it. What's
okay,
inside. Okay.
so you just do the opposite of the H, not the K.
Correct, because it's x minus h. So it'd be x minus -8. Now, there's something called the axis of symmetry, okay? And the axis of symmetry, let's see, the vertex here is what, -8, 3, okay? The axis of symmetry is a dotted line that goes through the vertex. So since the x value here is -8, the axis of symmetry is at x equals -8, which means that the graph is going to be symmetric. So whatever happens over here is going to, the same thing's going to happen over there. Or if it looks like that, it's going to look like that. It's going to be symmetric about that line. Okay. But the axis of symmetry is described as an equation, x equals, because it's a vertical line. Now, what I want to do, and I know I don't have a whole lot of time here, is I want to go into WebAssign and I want to look at, give me just a minute here. I don't want that. Okay, let's see here. Let's take a look at this. I know you can't see it yet. Let me get it to where I want it here. Let's keep going. Okay. Can you see the WebAssign screen now?
Yes.
Okay, so this is important because if you don't do this right, your graphs won't turn out correctly. Determine the vertex and axis of symmetry of the graph of the function. Okay, now the vertex would be at HK. So what is H?
Negative.
It's 3.
Why?
It's in the form, okay, it says x minus 3. So it'd be x minus
Oh,
H.
the opposite.
Okay. And what's the y value? It's 2. Okay. Now, the axis of symmetry is going to be x equals 3. And time again, people get this wrong because all they do is they put in 3 and it's got to be an equation. X equals 3. Okay. Now, here's the critical part. To graph the equation, which is also a function, you have to graph, in WebAssign, you have to graph 2 points. The first point you graph is the vertex. Okay. So I'm going to click here till it turns blue. And I'm going to click on the vertex 3, 2. I'm not going to use the points. I'm going to use the parabola. Now I need a second point. Okay. So let's pick a point that we can just calculate. Let's say that x is 0. Okay. If x is 0, what's 0 minus 3? What's 0?
Negative
minus-
3.
What's negative 3 squared? Negative 3?
9,
9. What's 9 plus 2?
11.
So when x is 0, y is 11, right? Okay, so that's another point on the graph, 0, 11. And I'm going to click there, and there's my parabola. Okay, now if you're graphing freehand on a piece of graph paper, you've got to find way more than that. You've got to find the vertex and several points to get the shape. But in WebAssign, all you need is the vertex and one other point. But here's the problem, okay? Let's say I do it backwards. I don't plot the vertex first. I go, let's see here, and there. I plot a point and then the vertex. Oh, that's not the right picture, is it? That's upside down. It's supposed to look like this. So it's critical that you graph the vertex first. Okay, so there's the vertex, and then I find one other ordered pair, and there's my graph, and let's see what it says. Yay, it's correct. Okay, so when graphing, you find the vertex and then another point on the graph. When you plot it, you start with this and you plot the vertex first and then the other point. Okay, and don't forget, just like last time, you can go, like when we graphed a linear equation stuff, you can go in here and adjust the points if you need to. Okay, all right, time's up. I know I crammed a lot in there, especially at the end. I'll be back at 1:15 today if you have any questions. I'm going to go ahead and stop the recording.